Thank you for your introduction. And good afternoon, everyone. My name is Vibol from Tokyo Metropolitan University. This work was mainly conducted by our graduate student, Mr. Tashiro from Ikei Laboratories. And again, my talk title is Live Stereoscopic 3D Image with Constant Capture Direction of 360-degree camera for high-quality visual telepresence. First of all, let me introduce our concept background. When we view a live video, that camera lens direction rotated. We are easily to feel sick to view rotate video. But if we keep the direction of the lens constant, even though there are a few translation, but we still feel fine to view the video. And here is our motivations. We aim to develop a telepresence camera system with highly accurate depth perceptions, low motion blur, and low visual sickness. To realize that, we use 360-degree camera for each eye of viewer. And as our concept, we want to keep the lens direction constant, so we develop a mechanism that can fit the camera direction even though there is rotated along with the head rotation. And in the previous camera system for telepresence, most of them use two cameras for stereo visions, but because each lens direction was not constant, it rotated along with the rotation of the head. It easily to produce high motion blurs and may cause visual sickness. Another method of telepresence camera system is using one omnidirectional or 360-degree camera. It is popular method because it can provide more immersive, more realistic sensation, and it also can reduce motion blurs or visual sickness by fixing the direction of the camera. But because it's mono visual, it's kind of mono vision, so the problem of low accuracy of the perception still remains. And here is our method that we propose to overcome this issue. We use two cameras for high accuracy of depth perception, but we did not allow this camera lens to rotate along with the head rotation, the same as that held down in the, As the conventional parallel camera, both camera lens rotate, but in our proposed method, we keep the lens camera constant. And here is our real system. We call it TwinCam. And as you can see, even though the camera rotates along with the position of the eyes, but we keep the lens direction constant in the world coordinate. And actually, it's a very simple idea, and but I think it's smart, and I like it. It's not mine, but I like it. And we also conduct a simulation to confirm that, to investigate that our camera system can reduce motion blur during head rotation. As you can see on the left side, it's a conventional parallel camera. When the head rotates, the camera lens also rotates. And then the position of the center pixel quickly change on the screen. And when the screen becomes far and far away, the velocity of the center pixel will be increased. So it indicates that the conventional parallel camera can easily produce the motion blurs. In contrast, on the right side, animation show that when we keep the lens constant, even though the screen becomes far and far away, but the velocity not much change. So we can consider that our proposed method can reduce the motion blur. We also did a simulation to prove that our method can compensate the latency of motion to photon. Suppose that when we rotate our head quickly in 90 degree as a step function, because we use 360 degree camera, the image appears quickly on the HMD screen. So it takes only T1 in a short time. But for the conventional parallel camera, it takes other time for send the command to the camera system and then receive the image back. It's a time of T2, T3, and T4. But to receive the correct image of bicular duplicity on the HMD, our system also requires T2, T3, and T4. We conduct 3 kinds of experiments to evaluate our system. And the first experiment is to compare the error of depth perception by binocular Q of our TwinCam to that by conventional monocular camera. There were 6 males, aged from 22 to 23 years old, participate our experiment. They were HMD and used a rod to adjust the distance of the right side paper. Also here. The right side paper to the distance that it the same as the reference paper, because they can compare the distance by the size of the paper, so we do not use the same size of the 2 papers. The right side paper is A4, but the reference paper were twice of A4, half of A4, and quarter of A4. We also set 3 conditions of observation angle is 0, 45, and 135 degrees. And here is the results of our experiment 1. There is the vertical axis represents the depth perception error, and the horizontal axis is observation angle. According to the result, the result showed that the depth perception of TwinCam system was far more accurate than that of monocular condition. So we can conclude that only one 360 camera is not enough to provide the correct depth perception. So stereo vision is still required for high accuracy of the perception. Next, we conduct experiment 2 to evaluate the motion blur during rotation. During rotating the camera and capturing a screen of black and white vertical stripe. There are 2 kinds of camera system. The left one is conventional parallel camera, and the right one is our TwinCam. We set screen to 3 different distance, 460, 600, and 10 millimeter far away from the camera. Also, we set the different speed of rotation from 1.19 to 6.73 radian per second. Here is an example when we capturing the screen. It's hard to see, but we can do that on the left side conventional parallel camera, like producing more motion blur. And here is the real capture that we crop the image, and we calculate at intensity and also histogram. And according to this result, we can observe that when the rotation speed becomes faster and faster, the group image the motion blur, we observe the motion blur on the group image. And here is for the motion blur that we capture by our TwinCam. For our method, we observe that even though the rotation speed become faster, but the motion blur did not increase. Here is the summary of our results. We also calculate the contrast, and according to these results, we saw that our TwinCams, the contrast keep constant even though the speed more faster for our TwinCam conditions. But for the conventional parallel camera, especially when the screen become far and far away, the contrast value slightly decrease. So according to this result, we can conclude that the motion blur did not occur with our TwinCam, but it easily occurs with conventional parallel camera during quick hit rotation. And the last experiment, we interested in VR sickness. We compare the VR sickness produced by our TwinCam to that by conventional parallel camera. There are two kinds of latency. One is 390, it's original latency, and we add additional latency, it becomes 640 milliseconds. 1 female and 12 female, each from 22 to 24, participate our experiment. We asked them to view each of 7 targets, and after 30 head turn in 60 seconds, we asked them to score the SXU level. And here is the results. The vertical axis represents the SXU levels, and the horizontal axis is camera configuration. We found the both main effect of camera configuration and latency. And according to these results, we can conclude that our TwinCam produce low VR sickness than conventional parallel camera. And when the latency become higher, the level of VR sickness also become higher. Here's the conclusions. We developed a TwinCam for Telepresence, and our results show that our system produce highly accurate depth perception, low motion blur, and low VR sickness compared to the conventional parallel camera. And our future work, we want to attach our system to the movable robot or vehicles. And here is the last of our slide. I am happy to hear any comment and questions. Thank you.
I'd like to have some questions, comments from the audience. Any questions or comments? Okay, so I have some questions. I think this movement of the TwinCam is actually not completely the same as when we are looking around by using binocular eyes. But in this sense, there might be some sort of drawbacks might be existing. So do you have any drawback? So even though you can avoid the motion blur by moving this camera, so you have to have, for avoiding the rotation. So that might be a good point for the avoiding motion blur or such kind of things. But is there any other side effect?
You mean other movement direction?
Yeah.
Yes. Actually, for the jaw rotation, it's fine, and for the pitch rotation like this, because the position of eye and the position of camera then is the same is okay, because when we move like this, we just use the image position. But the problem is move like this because the position is different. One is low and other one is high. We consider about it too, but we do not yet how to make mechanisms. Another one, when we attach to the movement, for example, robots, because we will change many directions and we will consider in our future work.
Okay, I see.